Assalamualaikum and a very good day to the respected panel of examiners. My name is Zani Azri. Today I am pleased to present my final year project for Csp650 titled Dynamic Network Slicing for 5G Campus Network Performance Optimization. So I would like to extend my deepest appreciation to my supervisor Puan Nur Azilia binti Ahmad Azam for her invaluable support and guidance throughout this research. To begin, let's take a look at the project background. 5G technology serves as a critical milestone for smart campuses by offering high-speed, low-latency connectivity capable of supporting e-learning, administrative staff, and IoT sensors simultaneously. By utilizing network slicing, a single physical 5G infrastructure is divided into virtual layers tailored to the specific user groups, ensuring that diverse performance requirements are met within a shared network environment. This brings us to the core objective of this study. To achieve this, three main objectives were formulated: to design and simulate a 5G campus network topology with multiple network slices for students, staff, and IoT devices; to implement a dynamic network slicing mechanism that adapts bandwidth and resources based on real-time traffic condition; to evaluate the performance of static and dynamic network slicing in terms of throughput, latency, resource utilization, and quality of service. Now, why is this dynamic approach necessary? Because modern university campuses frequently experience highly unpredictable, localized traffic spikes. Under this condition, traditional static network face three major issues, and that is rigid allocation, where traditional networks rely on static bandwidth allocation, making them unable to adapt to the sudden unpredictable traffic spikes common in university environment. And then resource inefficiency. Static assignment often leads to packet starvation for congested user groups, while bandwidth assigned to inactive groups sit idle and is wasted. And the last one is degraded experience, the inability to automatically shift capacity during localized congestion events that ultimately degrades the quality of service and overall user experience. To address this issue within a clear academic boundary, the project scope is defined as follows. First is simulation environment. So this project utilized Mininet with no physical 5G hardware or live user deploy. Network architecture. SDN based virtualized campus topology divided into student, staff, and IoT segment. Slicing implementation deploys EMBB, URLLC, and MMTC slices to compare static versus dynamic bandwidth allocation. The last one is evaluation metrics. Performance is strictly measured based on throughput, latency, and overall resource utilization. Finally, the significance of this research cover four key aspects. Performance optimization, where demonstrate how dynamic slicing directly reduces congestion and improves overall campus network speeds. Resource efficiency, it validates real-time bandwidth reallocation to maintain high quality of service. Cost-effective research, provide a practical, hardware-free simulation model highly suitable for academic and campus network testing. The last one is bridging theory and practice, expand the understanding of autonomous 5G network behavior without the high cost of physical deployment. Moving on to research gap and related work, I reviewed several recent studies to frame my research, while authors like Zhang et al. And Li et al. Explored 5G visualization and multi-access edge computing. Their work lacked a specific campus deployment scenario. Furthermore, studies by Kumar and Rahman investigated slicing using AI and SDN controllers, but they lack real-time performance monitoring or direct before and after comparison. So my proposed solution specifically bridge this gap. So it delivers a dedicated campus-based slicing model utilizing SDN and visualization, complete with comprehensive performance testing and real-time bandwidth optimization. So this use case diagram illustrates the operational flow of the system. The primary actor is the network administrator, who interacts with the 5G Dynamic Slicing Manager. The administrator role begins by configuring network parameters, initializing the slices, and executing the simulation. Once the network is live, the automated system takes over the core functions and monitoring real-time traffic, detecting congesting events, executing the dynamic bandwidth reallocation, and finally analyzing the performance comparison. To ensure the structured development process, I utilized the iterative waterfall model. The project followed by a logical sequence starting from information gathering and problem identification down through the designing the topology and developing the slicing logic. So the crucial iterative step occurs during the performance testing phase. If the network simulation produces error or fail to dynamically allocate bandwidth, so the system allowed for iterative troubleshooting of the RU controller logic. Once performance metrics were successfully met, the project proceeded to the final documentation stage. Okay, this brings us to the live system demonstration where we put the SDN architecture to the test. Assalamualaikum and welcome to the live demonstration of my 5G dynamic network slicing project. So on the left, we have our mininet environment and view SDN controller, these two tabs. And on the right, we have the live Grafana telemetry for student slice A. Okay, to demonstrate the dynamic slicing algorithm, I will simulate a sudden network congestion event. First, I am setting up a listening server on a staff host on the background. Okay, as you can see, I have already setting up the listening server. And now, next, I am executing a heavy UDP traffic flood from a student host across the core switch to simulate a massive spike in campus user. Okay, as you can see here, uh, if we look at the controller logs, the SDN controller instantly detect the traffic that has breached the safe threshold, so it autonomously triggers the elastic donor pool algorithm at this part here, and the bandwidth are allocated and upscaled to 15 Mbps from 5 Mbps. So over on the Grafana dashboard, you can see this happening in real time. Okay, at this part, from the 5 Mbps, it goes to 15 Mbps, and speed are increasing. So this is safe. This safely absorbing the traffic spike and preventing packet starvation without any manual intervention. So, as the traffic drops back to normal, as you can see, it's already done in, I test it in 1 minute. So 1 minute has gone. So the traffic load, the controller sense the stable network condition and it automatically recovers the borrowed bandwidth and reset the student slice A back to its safe 5 megabits per second baseline. So this confirms that the SDN based dynamic slicing architecture is 100% autonomous, elastic, and ready to optimize 5G campus network. Thank you. As you just witnessed in the live video demonstration, the slide captured the exact moment of the dynamic scale up. When I initiate the heavy UDP traffic flood, the load on the student slides instantaneously spiked to 13.5 megabytes per second. So this screenshot from the Grafana dashboard confirms how the SDN controller reacted in real time. So it instantly detected the threshold breach autonomously, borrowed capacity from the donor pool, and upscale the allocated limit from our 5 megabytes per second baseline up to 15 megabytes per second. So this proof the system ability to completely prevent packet starvation under sudden stress. Okay, following that event, this slide highlights the automated baseline recovery that concluded our demonstration. Once the simulated traffic flood was stopped and the congestion cleared, the SDN controller immediately sends the drop in packets as captured here in the dashboard. The system automatically reclaimed the emergency bandwidth without a single manual command. It smoothly reset the student slice back to its safe 5 megabits per second baseline, proving the architecture is fully self-healing and elastic. To summarize this finding, this table highlight the performance comparison between the traditional static QoS and dynamic SDN slicing model, where traditional network enforce rigid limits that lead to high packet drops during spikes. Our dynamic model is elastic, reallocating resources from a donor pool. Furthermore, while static network requires manual intervention to fix congestion and often waste idle bandwidth, this dynamic architecture achieves 100% autonomous recovery and maximize overall resource utilization. So, in conclusion, this project successfully deployed an autonomous SDN-based dynamic slicing architecture designed to optimize 5G campus network by implementing an elastic donor pool algorithm in a simulated mininet environment. The system proved that dynamic bandwidth reallocation significantly outperformed traditional static quality of service methods during unpredictable traffic. The controller demonstrated real-time scalability by seamlessly boosting capacity to prevent packet starvation and automatically resetting the baseline limits once congestion cleared. Ultimately, this finding validates software-defined automation as a highly practical, efficient, and scalable framework for ensuring continuous high-quality performance in dense university infrastructure. That brings me to the end of my presentation. Thank you very much for your time and attention. So let's create innovation that makes an impact. Thank you.